This video is on Equilibria. So the aims for this video are to be able to construct an expression for the equilibrium constant, that is Kc, when given chemical equations. Use this Kc expression to form calculations to predict the effect of changes in conditions on the equilibrium constant, so changes of conditions to the equilibrium on the Kc value, and particularly you're going to look at temperature, and to work out the units for the equilibrium constant. They change depending on the equilibrium expression. So the first thing you have to be able to do is construct an expression for Kc. So I'm just going to give you a random generic equilibria. So we've got some reactants, 2A plus B, in equilibrium with some products. So for example, 3C plus 2D. And Kc, the expression of Kc is a fraction, and on the top of the fraction you have the concentrations of the products multiplied together. And because there are 3 C's and 2 D's that are made, we have to multiply 3 C's together and 2 D's together. But when we write it in the expression, remember that square brackets mean the concentration of. We can just put C as being cubed, that's 3 C's multiplied together, and the concentration of D as being squared, because there are 2 of them times together. On the bottom are the reactants all multiplied together. So in this case we have 2 A's, which would be multiplied together to be A squared, or the concentration of A squared, and 1B. So that would be your expression for Kc, and basically what this expression tells you is how far to the left or right this equilibrium lies. So if Kc was increased, or was a bigger number, then that would mean that this top number would be bigger, and so therefore the equilibrium must lie on the right. If it was a smaller number, then this means the bottom number must be bigger compared to the top number, and therefore the equilibrium would lie to the left. So that's why Kc is an important number when looking at equilibrium. So to put that into practice then, we're going to look at this past exam question. So here we're going to use the equilibrium constant to perform calculations, and in this past exam question they're asking you to work out the concentration of Q in this equilibrium mixture based on these values. Now, we can work that out using the Kc expression. Now usually past paper questions will ask you to work out a value for Kc using concentrations. But in this case, I've chosen this one because it's slightly different. We're working out a value for Q. So the first thing you've got to do is write an expression for Kc, which I'm just going to do at the top of the screen. So remember that Kc equals the concentrations of the products multiplied together. So in this case, we've got 2 R's that are being made, so we've got R squared, divided by the concentrations of the reactants multiplied together. So the concentration of P multiplied by the concentration of Q squared, because there's 2 of them. Now, because we're trying to work out the concentration of Q, we want to rearrange this expression to get Q by itself. So the first thing you do is multiply by the whole of this on the bottom to get R squared by itself, to multiply out the division first. So what we'll get is Kc concentration of P times the concentration of Q squared equals the concentration of R squared. The next thing we do is divide by Kc times the concentration of P, so that will move onto this side, so divide by Kc times the concentration of P, and then to get rid of this squared, we've got to square root, so the square root of this will equal the concentration of Q. So now we've got to get values for concentration of R and concentration of P. We've already been given the value for Kc, which is 68. Now you've got to be careful here because the values for P and R have been given to you as moles, but remember that the square brackets represent the concentration of them. So you've got to use this volume as well to first convert these into concentrations. So if I just do that on the side here, so the concentration of P is going to equal 3.82. Remember, concentration equals moles divided by volume, so 3.82 divided by 10. Our volume is 10 decimetre cubed, and the concentration of R is going to equal 5.24 divided by 10. So the concentration, therefore, the concentration of P will equal 0.382, and the concentration of R is going to equal 0.524. Now, if we put those into the expression to work out the value of Q, it's going to equal the square root of 0.524 squared divided by value for Kc, which is 68, times the concentration of P, which is 0.382. And that will give you a value of 0.103. And then remember to put units, and it's going to be moles per dm cubed. So now we're going to look at predicting the effect of changes in conditions on the equilibrium constant. So to do that, we've got to have the equilibrium constant in front of us. So it's the same equilibrium as before. So here we've got Kc equals, remember it's the product of the concentration of the products. So there we've got R squared divided by the product of the concentration of the reactants. So that's concentration of P times the concentration of Q squared. Now what you've got to be aware of is whether the reaction is endothermic or exothermic to the right and to the left. So here we've got a delta H value, and it tells you it's minus 50 kilojoules per mole, and that means it must be exothermic to the right hand side, and therefore endothermic to the left. So let's think about what happens if we change the temperature. If we were to increase the temperature, then the equilibrium is going to shift to the side that reduces the temperature again, so therefore the endothermic side. So if we was to increase the temperature, then the equilibrium would shift in this direction to the left. Now if this equilibrium was to shift to the left, then the concentrations of P and Q would increase, which means this bottom number of the Kc expression would increase, and therefore Kc would decrease. If, however, we were to decrease the temperature, then our equilibrium would shift to the right, and so more of R would be made, and the concentration of R would increase, which means this top number would increase, and therefore Kc would increase. Now this is going to be different for different reactions depending on whether it's exothermic or endothermic to the right hand side, but the principle will remain the same. So if we look at what the exam paper actually looked like, so here are the questions. So the first question, state the effect, if any, on the equilibrium amount of P of increasing the temperature, all of the factors are unchanged. So here is just as simple as Chatelier's question. It asks you to state basically what happens to the amount of P when you increase the temperature. Remember that this delta H value tells you that it's exothermic to the right hand side. So therefore, if we were to increase the temperature, then our equilibrium would shift to the left, so our amount of P would increase. Next question, state the effect, if any, on the equilibrium amount of P of using a container of larger volume. All the factors are unchanged. So, if we're using a larger volume container, then that means that we are decreasing the pressure, because we're giving the gas particles more space to move around. If we're decreasing the pressure, then the equilibrium will shift. Remember from Chem 2, the equilibrium will shift to the side where there are more moles, because it will want to fill that space again. So again, our equilibrium is going to shift to the side of more moles. On this side we've got 3 on the left, on this side we've got 2 on the right, so it's going to shift to the left hand side. So our amount of P will again increase. Then our last question, state the effect, if any, on the value of Kc of increasing the temperature. All other factors are unchanged. So if we increase the temperature, as we said before, it's going to shift to the endothermic side to decrease the temperature again. So it's going to shift to this left-hand side again. We've just got to look at Kc. So Kc equals the concentration of R squared over the concentration of P times the concentration of Q squared. We've said the equilibrium is going to shift to the left-hand side, so therefore this bottom number is going to increase, and if the bottom number of a fraction increases, then the result will decrease, so Kc here will decrease. Now it's important to remember that the only thing that will affect Kc is the temperature. If we increase the pressure or decrease the pressure, or if we increase the concentration of something, they will not affect Kc, because our ratios of these, the concentrations, will stay the same. The only thing that will change Kc is changing the temperature, and need you to remember that. So the final thing I'm going to talk about in this video is working out the units for Kc, which often you'll need to be able to do. So here we've got another example generic equilibrium. So we're just going to write out what Kc is again. So Kc equals the concentration of C squared times the concentration of D over the concentration of A cubed times the concentration of B squared. Now, in order to work out the units, we've got to think about what's happening with the units for these concentrations. So all of these concentrations have the units moles per dm cubed. So if we were to write moles per dm cubed in place of this, we'd have, for C, moles per dm cubed, and I'm going to write that moles dm to the minus 3 squared, times moles per dm cubed over moles, this is for A this time, moles per dm cubed times moles per dm cubed squared. Now the first thing we've got to do is cancel out the concentrations that cancel out. So here's we've got moles per dm cubed squared here, and we've got a moles per dm cubed squared there. So those cancel out. Then this moles per dm cubed will cancel out with one of the ones on the bottom. So this 3 here will change to a 2. So therefore our units for this Kc expression will be 1 over moles per dm cubed squared, which, if you write it out, will be moles to the minus 2 dm to the 6. On occasion, you might get units that might get a Kc value that has no units, and that's where you'll have the concentration, the powers of the concentrations on the top equaling the powers on the concentrations on the bottom, and that's fine. You just have to write no units. So the units for Kc will be different every time depending on the powers in the expression and what you're multiplying by.